Alright, today we're going to look at another step in our introduction to derivatives where we're looking at using the definition of a derivative, what our book often refers to as from first principles. We're going to find the derivative of some functions using this definition. Just for a quick reminder, remember we looked at finding the slope between 2 points on a curve by expressing the second point as this x plus delta x, f of x plus delta x. Then we looked at it as we got closer and closer and closer to that point. We could find the rate of change at a specific point if we took the limit as this delta x approached 0. Alright, so we have this definition of a derivative. Notice the notation here, the derivative with respect to x, or f prime of x, is this value here. Remember, we're simply using the slope formula and then finding the limit as the second point gets closer and closer and closer to the point that we want. So that's what we're going to do. That's what we're going to do today with a couple of these functions. If I can actually get on the right document here. There we go. Alright, so let's look, first of all, I have my definition here. A couple of things with the wording. Like I mentioned, from first principles simply means using this definition. The gradient function of f of x, that's simply their way of, another way of saying find the derivative. Now, one thing to keep in mind here is that derivative gives us the slope, hence gradient, of the function at each point. Okay, so some of these we can actually do without having to use the first principles or even any other formulas. For example, you see number 1 here, that's a line. If f of x equals x, that's a line, y equals x. Well, the slope is always the same on a line, and the slope in this case is 1, so f prime of x equals 1. Number 2 is similar. Here we have the line y equals 5. Well, that's a horizontal line. Horizontal lines have a slope of 0 because they're neither increasing nor decreasing. So we would say f prime of x equals 0. And that's actually true for any constant. Alright, so if you have a line, the slope is the same all the time, so the derivative is a constant. If you have a constant as your function, the derivative is 0 because there is no change on the function anywhere. But then we have these two down here, x cubed and x to the fourth. And I'm going to start with x to the fourth here. And one of the most challenging things of using this first principles is finding this f of x plus delta x part. So I always do that separately. And this is where it's helpful to remember your binomial expansion. If we quickly do Pascal's triangle. Whoops, I messed that up. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Alright, we're doing it to the fourth power, so we need this fourth row. And what we end up with is an x to the fourth plus 4x cubed delta x plus 6x squared delta x squared plus 4x delta x cubed plus delta x to the fourth power. That is the f of x plus delta x. Now we need to plug that into our formula. Alright, so I'm going to cheat a little bit here. Okay. So we have that whole thing minus our f of x. F of x is the original function, so x to the fourth. And that's over delta x. Now notice we're taking the limit as delta x approaches 0, so we can't just evaluate because we have a delta x in the denominator, and obviously that would be undefined at 0. So what we need to do is, just like with other rational expressions that we're taking the limit of, if the denominator is going to be 0, we want to see if we can somehow cancel out that denominator. Is this an asymptote, or would it be a point discontinuity? And in this case, finding derivatives, if it is differentiable, we'll always be able to cancel that out. And as you see here, we have an x to the fourth minus an x to the fourth, and then what's left up here, you'll notice all of them have at least one delta x. So there's a common factor in my numerator right now. What I'm going to do is actually cancel out 1. I'm going to cancel out that common factor. Now that's going to be a delta x squared. That's a delta x cubed with my denominator. So now I'm taking the limit of simply a polynomial, 4x cubed plus 6x squared delta x plus 4x delta x squared plus delta x cubed. And because all polynomials are continuous, we can simply evaluate now. Alright? If we plug in a 0 for all the delta x's, notice all these terms equal 0, and we're left with just 4x cubed. That is our derivative of x to the fourth. Okay? So f prime of x for x to the fourth is 4x cubed. Okay? So that's for x to the fourth. I'm going to do this one more time with our x cubed, and hopefully we'll be able to see a pattern here. Okay, so let's get rid of all of this. Obviously, if you need to see that more, you're welcome to pause it and go back. But let's take a look at what f of x plus delta x is. Since we're doing x cubed, we need this row of Pascal's triangle now. So we have an x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. Alright, so once again, we're going to plug that into, eraser, we're going to plug that into our definition for the derivative. Alright, there's in the numerator minus the f of x all over delta x. Okay, and you'll notice once again the x cubed will cancel out the x cubed, and we'll be left with terms that all have a delta x in them. So we can cancel out the delta x in the denominator with the common factor of delta x in the numerator. Okay, that leaves us with the limit as delta x approaches 0 of the polynomial 3x squared plus 3x delta x plus delta x squared. Once again, since it's a polynomial, we can evaluate, and these terms, when we plug in 0 for delta x, will be 0. So we have now 3x squared. That's f prime of x. Now, I've gone through 2 of these, and obviously we could do more to recognize a little bit more of a pattern. But I want you to see the pattern emerge here. We already talked about a line always has the slope of the line as its derivative. We said the constant function is always going to have a derivative of 0 because it's not changing. But you'll notice here what happens when we had an x cubed, you'll notice the 3 became the coefficient. Also, when we had an x to the 4th, the 4 became the coefficient. And then look at what happened to the power. The power was decreased by 1 in both cases, from an x cubed to an x squared, from an x to the 4th to an x cubed. So, if we want to predict a formula for f prime of x, whatever the exponent is, n will go out in front as the coefficient, and then we'll decrease the power by 1. So it'll be n times x to the n minus 1. Okay? You'll notice here it says n is an element of the natural numbers. That's 1, 2, 3 on up. However, as we'll look at later, this would also apply for n being any real number. So we can extend it there. Now, taking this one step further, we can look at other polynomial functions and take the derivatives of these. Okay? Now, if I wanted to take the derivative of this function x squared plus 3x minus 5, I would need to do f of x plus delta x. So I would plug in an x plus delta x for x. So I'm going to get x squared plus 2x delta x plus delta x squared plus 3 times x plus delta x. So that's going to be 3x plus 3 delta x. And then minus the 5. Alright, so this whole thing is our x plus delta x. Okay. So I'm going to take that and put it into our definition of a derivative. Notice now I have to subtract the entire original function. So I'm subtracting the x squared, I'm subtracting the 3x, and I'm subtracting the negative 5. So it's a plus 5. And of course this is all over delta x. Now watch what happens. We have an x squared minus x squared, that's 0. We have a 3x and a minus 3x, that's 0. We have a minus 5 and a plus 5, that's 0. And you'll notice what's left in the numerator are the terms that had delta x's in them. So, if we cancel out that common factor, do that, it's going to cancel out one of those, it's going to cancel out that one. I'm left with the limit as delta x approaches 0 of a 2x plus delta x plus 3. Okay? 2x, delta x, and 3 are all that's left in my numerator. You'll see that is actually a polynomial function which is continuous everywhere. Therefore, I can evaluate, which means the limit is simply a 2x plus 3. That is our f prime of x in this case. Okay? Now what does that mean? Well, that means that I can find the slope of any point on this graph, which would look something like this. Actually, I think it would be more... the vertex would be on the other side of the y-axis. So it would look something like this. Any point on this line is going to have a slope of whatever the x-coordinate is times 2 plus 3. Okay? So it asked us for the rate of change at x equals 4. So if we come over here to where x is 4, what's the slope of that tangent line to the curve? Well, if we do f prime of 4, then we get 8 plus 3 which is 11, which if you look at the graph makes sense because it's going sharply upward. Alright, so how can we apply what we saw back here to what we're doing here? Well, it goes back to the limit theorems that we talked about earlier. When we were taking the limit of a sum, we were able to take the limit of each addend of that sum. So for example, if I were finding the limit of f of x as x approached something, I could separate that into x squared, the limit of x squared, the limit of 3x, and the limit of negative 5. Okay? Well, because a derivative is just a big limit, then when I'm taking the derivative of a sum like this, I can also find it by taking the derivative of each portion. Okay? So, I know we already know what the answer is. It's 2x plus 3, but let's look at y using this rule. If I take the exponent 2 and I make it the coefficient of x, and I decrease the power down to just x to the first, I've got a 2x. Well, now if I look at the 3x, that's a linear portion. Well, the slope of a line at any point is the same, so in this case, the slope is 3. So, the derivative of 3x is 3. So I'm going to add that to the derivative of x squared. And then I have this constant, negative 5. That's a constant. The slope of a constant is 0 because there is no change. So that's 0. So 2x plus 3 plus 0 is just 2x plus 3. And you can see how we applied the rule that we had before, along with our understanding of limits, to come up with our derivative without having to do all this work. Okay? So, hopefully that's helpful, and that's how we can find derivatives of basic polynomial functions.